everyone. And so today I'll talk about resilient representation and provable generalization. So as everybody here knows, deep learning has making great advances, has beat humans in Go, achieving human-level performance for image recognition. It's helping us in our everyday life, and also even helping saving energy in data centers. However, without that, on the other hand, as some of you may have seen, these deep learning systems are also very easily fooled. So this, I'll just go over this very quickly. Many of you may have already seen this. So the left column are the original image that the neural network image classification system correctly classifies. And the middle columns are the adversarial perturbations. So these are perturbations that are specifically constructed by the attackers. And these are magnified so you can see, but otherwise they're actually very, very small. On the right-hand side columns, so these are what's called adversarial examples. So these are essentially the original image with the adversarial perturbation added. And as you can see here, these adversarial examples cause the image classification systems to misclassify. And as it turns out, these type of adversarial examples also exist in the physical world. So for example, you can generate the adversarial examples, you can print them out, and then take a photo. And the photo of the adversarial examples also often remain adversarial as well. And such examples can cause a lot of potential issues when we have autonomous systems. This is just an example in autonomous driving. So here, again, are two example images, two humans. They look almost the same. In fact, you probably can't tell the difference. But however, the top image is the original image, and the bottom image is the adversarial example with the adversarial perturbation added to the top. So for these two images, to the image classifier, the top will be correctly classified as a stop sign, but the bottom will be classified as a yellow sign. As you can see, issues like this can really cause potential danger in this autonomous driving scenario. So these are just examples showing adversarial examples for image classification tasks, and this has been actually the focus of most of the studies in adversarial examples in the community. So with our recent work, we actually have looked at the issue of adversarial examples in a more broader setting. And the short conclusion is that unfortunately, this adversarial example phenomenon is very prevalent in deep learning systems. And in particular, we looked at other tasks, for example, image captioning and object detection. We also looked at other threat models. Instead of assuming that the target model is known, which is called a white box, we also look at settings where the target model is unknown, the black box setting. And here, we actually demonstrated our attack also on public API cloud services, such as Clarify AI, which actually is a startup. Came, I think, out of NYU. A few years ago, they actually won the ImageNet competition as well. And we also look at the other model classes, including generative models and also deep reinforcement learning. So here, I'll just quickly show you a few examples. So this is an example of image captioning and object detection. And here are examples on the left-hand side. It shows the original image with the image captioning generated by the image captioning system, which looks quite reasonable. And on the right-hand side is the adversarial image. As you can see, to humans, they look quite similar. But the image captioning system will give you a completely wrong captioning. And actually, I got asked, when I talk to people about adversarial examples, oftentimes people do bring up this. Maybe generative models are better. So here's an example showing that actually generative models actually also have similar issues. So in this work, we looked at VE-like models for generative models like VE, VE-GAN, and so on. And for this type of generative models, there are two components, two stages. You have the input X that goes through an encoder, which produces the latent representation. And then you can feed the latent representation into the decoder, which tries to reconstruct the original input. And one application scenario you can imagine for this type of generative models is image compression. And there has been recent work also showing that neural network-based image compression is actually reaching state-of-the-art performance compared to traditional image compression mechanisms. So the setting of the adversary examples for this type of setting is the following, where the attacker is trying to generate adversary perturbation of an original input. For example, here, adversary perturbation of original input 7. And then after the compression and decompression stage, another image will be reconstructed, and the attacker's goal here is to have this reconstruction to be something completely different. In this case, for example, 8. And one security implication application for the setting is that as we know, we have like security surveillance cameras all over the place. And typically how these systems work is that they will record images, and then they will compress it and only store the compressed version, and they will throw away the original version. And as you can see with the attack like this, what could happen is that later on when the law enforcement comes to try to reconstruct, to run the decompression and to reconstruct the original images at the crime scene, then in this case, what the law enforcement may see may be completely different than the actual original scene. So now let's look at how effective these adversary examples can be for these generative models. So here's an example for the MNIST dataset. On the left up corner is the original images, and then on the right up corner, you'll see these are reconstruction of the original image. And as you can see, these reconstructions actually look pretty good. So the generative model is doing its job. So here the attacker, let's say the attacker's goal is to turn the perturbed version of the original images after the compression and decompression stage into something like the target image 0. So that's the attacker's goal. That's the target image. So then these are the generated adversarial examples. And then when you look at the reconstruction of these adversarial examples, you can see that these are got reconstructed into something very similar to the target image, into 0. And also we did this for street view and street numbers. Similar things happened. And also here's the example for the face data. As you can see, these attacks are actually fairly effective. So that's for the generative models. And here's the example looking at the adversary examples on learned deep policies in the setting of deep reinforcement learning. So these figure just shows that here we trained the A3C agent on the game Pong. And without the perturbation, here basically you can see that the Pong agent actually does very well, achieves max reward, which is 20. And then as you add perturbation, you can see that the Pong agent actually fails completely, pretty much reaches the lowest level of reward. And also, I'll show you the video in a second, which you'll see better. But one important point from this work, we also show that in this case, the perturbation that you need to add is really, really small. So after quantization, basically, most of the time you don't see any difference. After quantization of the image frames, then the attack version versus the original version are identical. But for the agent will completely fail for the attack version. And also in this case, given that this is a game, the attack actually can be much richer than if you just look at adversary examples, for example, for a static task like an image classification. So in here, we also looked at how the attacker can do smarter attacks. So the result I showed in the previous slide is where the adversary perturbation is injected into every frame. But that, of course, is quite costly in terms of what the attacker needed to do. So we also looked at how the attacker can be more intelligent in adding perturbation. So instead of adding it into every frame, it may only just need to pick certain frames to add and still have effective attack. So in this case, we showed that the attacker can use a value function learned from the neural network to guide when to add the perturbation. So it only adds a perturbation once the value function goes above a certain threshold. And then we show that in this case, even though the attack itself needs to only add a much smaller, it's just a small fraction, adds perturbation to a small fraction of the frames, but still the attack actually is very effective. And here's just a video showing the attacks. So this is the original frame. As you can see, the learned agent is actually quite good. And then, so this is the, with every, so this is the attack with the perturbation added to every frame. And as you can see, the agent basically just completely fails. And then this is the one where the attack is injected based on the value function. So it's only injected in a certain small fraction of the frames. But also, you'll see that the agent is a little better, but still it actually fails the game almost completely. Okay. So the results indicate that these learned policies are not resilient against these adversarial attacks. And this is an example also showing, giving a deeper look at in inspecting the what we call action decision space, essentially to look at how the learned policy actually look like in the space. So what this figure is showing, if we look at, for example, the left, in the center of the frame is the original input frame. And then with the 2 dimensions x and y, so these are dimensions of the perturbations that we add. So essentially spanning the plane are essentially input frames with various perturbation added according to the direction and the magnitude. And the x-axis is the attack direction, meaning the direction of the adversarial perturbation that we added, and the y is orthogonal random direction. And then each dot in the plot shows what's the action predicted by the policy, given that input frame. And from what you can see here is that actually this action decision space is very fragmented. So this is another indication to see why the attack is happening, and in fact, this action decision space is not smooth. If you just make very small changes, make small perturbations, the predicted action actually will change. So what this leads to is the question of resilient representation. So what we have seen so far for all these examples that I have given, we see a common issue is that the currently learned representations are not resilient against these adversarial attacks. So for example, so we all know the importance of learned representations. That's how, for example, in the image captioning, the hope is that you learn the representation, capturing the image, and then based on that representation, you can turn that into a captioning. And similarly, in the generative model, you try to learn a latent representation that captures the original inputs, and then later on you can use that to do reconstruction. And also, that allows you to do certain manipulation as well. But however, for all these systems, from what we have seen, is that unfortunately, these learned representations are not resilient against adversarial attacks. So I think this begs the question then, as how we can learn better representations, how we can learn more resilient representations. And also even before that, I think some important questions need to be addressed for the communities. We need to understand better what are the good properties that these learned representations should have. So in some sense, what you can say is that we want to have some kind of smoothness property for these learned representations. And of course, then the question is, what does smoothness mean here? And what is the distance metric that you want to use here to define smoothness? And in fact, this is part of the, I would say, the core challenge in this space as well, is that when we talk about smoothness, ideally in this case, we want to say, give an image, and then if you perturb it, to humans it still look the same, and hence you want the learned representation to still, essentially, you want to compute the same representation. But in this case, the distance metric we are using to say that the two, the input and the original input and perturbed input are similar, that's essentially, I would call here a semantic distance metric. You want to say, semantically, these two are the same. On the other hand, if you perturb the image in some other way, even though from L1 or L2 distance, they can be very small, but semantically they can be very different. And in those cases, we do want to say that the learned representation in this case should be different. But as you can see here, but in general, so far we only have these, L2, L1, L2, L0, L infinite, all these different distance metrics. But when we want to define, ideally, the smoothness in this case, we want to define it in some sort of semantic distance metric. But on the other hand, this is also exactly the problem that we want to solve, is that we want to figure out how to define the semantic distance metric. Because once we have that, then we can do similarity measures, and a lot of the learning problems will be solved. So that's, I would say, then this definition itself is not clearly defined, and hence it is an open challenge how we should have a better definition of this kind of smoothness metric. And also, another question related to is that, and one may say that one of the reasons that this kind of problems happen is that your test distribution is different from your training distribution. So first of all, this is not entirely the story. I won't have time to go into that because for some of these perturbations, they are so small, you cannot say that actually the test distribution is different from the training distribution. As I mentioned, in certain cases, like you can't even see the difference after quantization. So, but there is, I believe, separate from that point, I do think there is an important place for this question, as ideally we do want to be able to detect this, essentially also related to some of the questions mentioned yesterday, is that we want to have some kind of confidence bounds, knowing that the learning system should know under certain scenarios it's similar to the scenarios it has seen in training setting, and hence it can be more confident about what's its decision. But it wants to detect when the scenario that it's seeing now is different, then it has a lower confidence, and hence it may need to ask for help. Right. So I think this is an important question as well. So far I've talked about these adversarial examples and how prevalent the issue is. Then another question Yang would ask is, do adversarial examples matter? And why should we care about resilient representations? So first of all, the adversarial examples actually is just the tip of the iceberg. It's an issue in the broader field of adversarial machine learning. What adversarial machine learning is essentially doing learning in the presence of adversaries. So that's what the entire field studies. And the adversarial example in this case is essentially what happens at inference time in the presence of attackers. Then at inference time, the attacker can try to fool the learning system. And we call these also often evasion attacks. And similarly, the attack can also happen at other stages of the learning system, for example, at the training time. So one typical example of a training time attack is called a data poisoning attack, where the attackers are trying to poison the training set. Oftentimes, they're providing the poison labels to try to fool the learning system to learn the wrong model. A very funny example is you can view the Microsoft's Twitter chatbot as an example of this, whereas in this case, humans try to feed the Twitter bots these politically incorrect, outrageous statements, and that's what the Twitter bot learned and had to be taken down. And another example is with some of our earlier work, we show that actually in certain settings, the attacker doesn't even need to poison the labels. So even when the labels are completely correct, in certain settings, the attacker can select what training data points to show to the learning system, and in that way to try to fool the learning system to learn the wrong model. So overall, these adversarial machine learning issues, they are particularly important for security critical systems. And I would say that this is a hugely important question at the intersection between AI and security, which is essentially talking about AI in the presence of attacker. And it's really important for the whole community to consider the presence of attacker. for example, history has shown that the attackers always follow the footsteps of new technology development, and sometimes even leading it. And this time around, the stake is even higher with AI. As AI systems control more and more parts of the world, the attacker will have higher and higher incentives. And also, as AI becomes more and more capable, the consequence of misuse by the attacker will also become more and more severe. And hence, I would say I do strongly believe at this point that security will be one of the biggest challenges in deploying AI. So when we talk about security of learning systems, there are issues and challenges at many different levels. The first level is the software level. For example, we want to ensure that there are no software vulnerabilities, such as buffer overflows in the learning system. And the good news is that for this type of problems, essentially, it's a common problem that we have already studied a lot. For example, the existing software security and formal verification techniques are exactly designed to address these kind of problems. So at the software level, we have a good understanding of the domain. And the bigger challenges and the more open problems are in these other two levels, the learning model and the distributed level. So first, let's look at the various challenges for security at the learning level. So first, as I mentioned about these adversarial examples, these are just examples showing that one is that we are now learning resilient representations, and also it's showing that the architectures and approaches somehow do not have good generalization of security guarantees. So the question is then, can we design better new architectures and approaches with stronger generalization and security guarantees? And also, furthermore, could we, in certain cases, provide even provable guarantees? So this is a question that we have started to investigate. And here, I'll just give you one example of some of our recent work to demonstrate. So the example domain of our work in this setting is a limited domain in what's called the neural program synthesis, where essentially we are trying to learn neural networks that will perform certain programming tasks. So this is an example of addition, where you can provide examples of addition, and then you design some kind of neural program architectures. When trained with the training, that will get a learned neural program, which then can perform, in this case, the addition task. So when you give it a new test input, it can produce the test outputs. And there has been a long string of works in the space to look at, to explore different types of neural program architectures to solve these kind of neural program synthesis tasks, including addition, sorting, and so on. So however, for all previous approaches, they suffer from two main challenges. The first one is generalization. Oftentimes, these neural programs do not generalize well. Here's an example of a sorting task, where so this is the example of the NPI work from last year, which won the Best Paper Award last year, that they trained the neural networks for sorting, I think, up to 20 numbers. But then, as you can see here, it actually, so this is some previous work, even before this one, that it fails very quickly. It can now sort for numbers for 35 numbers. And with MPI, still it fails for sorting 16 numbers. Right? So that's challenge number one. Okay, that these previous neural program architectures do not generalize well. Challenge number two is that even if empirically you observe that the learned neural program has perfect generalization for all your test data, but still you have no proof of generalization. You don't know still, even after you can sort for 100 numbers, you still don't know how the neural network would perform when you want to sort 101 numbers. So the question is, how can we solve these challenges? So this is our proposed approach to address these two challenges, is by introducing recursion. And the goal here is to learn recursive neural programs. So recursion here and just means the concept of recursion is a fairly fundamental concept in computer science and math. And the point of recursion is that you can solve a larger problem by reducing it to smaller problems, so that through reduction rules. And then these smaller problems, the base cases are easy to solve and reason about. So in our work, we proposed it's important to learn recursive neural programs, especially for the domain that we have studied. And the way we learn the recursive neural program is essentially, essentially you need to have a mechanism where the problem needs to, for example, you learn a function that needs to call itself, and hence reducing the problem to a smaller problem. I won't have time to go into the details. So with this approach, then the advantage is then twofold. One is that the recursive neural programs, they learn much faster and they generalize better. And also more importantly, recursion actually enables a proof of perfect generalization when the neural program learns perfect generalization. So here's an example that's comparing to previous approaches. When we try to learn a recursive neural program, then we, with the same training set, we can generalize much better. And also, this recursion structure is really the key to be able to provide a proof of perfect generalization of the learned recursive program. And in fact, so we actually propose a verification procedure. Essentially, the one way to think about this is that the verification procedure will we have a notion of a verification set. It's a set of inputs, and that can actually cover all the base cases and reduction rules. And so by explicitly testing the learned neural program over this verification set, if the learned neural program passes the verification set, then by this recursion, then essentially we can actually provide a proof of perfect generalization. And in our case, we actually did this over different tasks, including the addition and sorting task, and also some new tasks such as topological sort. So what are the lessons learned from this? So first, I think one really important lesson is that program architecture actually is really important, not just for learning, but also it really impacts provability. And this is actually very similar to our experience in the traditional symbolic program domain. So in the symbolic program domain, we know that well-designed programs with good architectures, they are much easier to prove properties of. Whereas arbitrary programs, bad code, they are actually very difficult to prove properties of. So similar to these symbolic programs, I do strongly believe that for neural programs, for neural network systems, program architecture also is very important in terms of provability. And a corollary to that is that I think there's some caution to end-to-end monolithic neural networks. And these monolithic neural networks can be harder to train, to generalize, and to interpret. So also what we have seen here is that the recursive, on the other hand, recursive modular neural architectures can be easier to reason, prove, and generalize. And with our work, we have mainly focused in a specific domain, which is a neural program synthesis domain. Then the question is, how can we explore new architectures and approaches to enable strong generalization and security properties of broader tasks? For example, for more complex, like perception tasks, and so on. And ultimately, can we have probable guarantees of generalization and security properties for more general learning systems? So that's the first challenge for security at the learning level. And there are a number of other challenges, too. So a second one I would like to mention is how we can evaluate these systems. And in fact, we should evaluate these learning systems and the adversarial events, not just normal events. Again, here's a comparison to how we do security in traditional software systems. So in my security class, actually this is one of the key slides that I teach my students, is that there's this important distinction between regression testing versus security testing. So for regression testing, the goal is to run programs on normal inputs. The operation is you run programs on normal inputs with the goal to prevent normal users from encountering errors. However, for security testing, we actually want to run programs on abnormal adversary inputs, for example, fuzzing to generate these abnormal adversary inputs with the goal to prevent attackers from finding exploitable errors before the defenders. And for the security of the software system, it's not enough to just do regression testing, and security testing is actually really, really important. Then similarly, I think it's important to make a distinction between regression testing versus security testing for learning systems as well. Regression testing, again, this is what I think the machine learning community has been doing, is that, and also you can talk about this at two different levels, the training stage and the testing stage. So at the training stage, you can train on noisy training data to estimate the resiliency against noisy training inputs. And for testing, you can test on normal inputs to try to estimate the generalization error. And in fact, this is exactly how every machine learning paper reports their test error. But however, to evaluate the security of the learning system, regression testing is not sufficient. We actually need to instead look at the security testing. And here, at the training stage, we want to train on poison data, training data to estimate the resiliency against poison training inputs. And for testing, we want to test on abnormal adversary inputs, like the adversary examples that I mentioned, to estimate the resiliency against adversary inputs.
How can you guarantee resiliency against adversaries where you don't know what the next adversary is going to do?
Right, that's a very good question. This problem, similarly, we have in the traditional software system as well. So then ideally, in the end, we want to have, again, that's why I talked about earlier, the provable guarantees and so on. But still, even without that, still we wanted to make the distinction that still security testing is important beyond just regression testing. And then furthermore, I think an even bigger challenge and open question is how can we reason about these complex non-symbolic programs? So for symbolic programs, this is what we have experience with for decades, operating systems, file system compilers, and so on. And these programs, their semantics are defined by logic. And as a whole community, there's a whole community of software verification, program verification, where people have developed decades of techniques and tools for analyzing and reasoning about these programs, such as theorem provers, SMT solvers, abstract interpretation techniques. And part of my career has been focusing on problems like this as well. And thanks to all these decades of experience and techniques and tools developed, it's actually great to see that now we actually have entered what I call an area of formally verified systems. So we actually have formally verified systems in, for example, microkernels, file systems, distributed systems, compilers, security protocols, and security systems. And thanks to the powerful formal verification tools developed for the past decades, and also very dedicated teams. Right? So some of these formally verified systems actually takes tens or even up to hundreds proof man years to do. So you really need a very dedicated team. So even though for symbolic programs we still have a long way to go, but at least we've had decades of experience and techniques developed for this. But unfortunately, when it comes to the learning system, I call these non-symbolic programs, like the neural networks and so on. And for these kind of programs, systems, we have very little experience in this domain. So for these non-symbolic programs, oftentimes we don't have precisely specified properties and goals, like perception tasks. And we don't have good understanding of how these learning systems work, like how neural networks work. And oftentimes, these traditional symbolic reasoning techniques do not apply. So these really pose a huge challenge in terms of how we can better reason about these complex and non-symbolic programs. And then furthermore, we need to reason about how to compose these components. I think Leon Bartel also, in some of his early talks, mentioned about this as well. As in general, the way to build large complex systems is through compositional reasoning, where each component provides some abstraction, and then we have this hierarchical compositional reasoning to prove properties of the whole system. But the question is, for these non-symbolic programs, how can we do abstraction and compositional reasoning in this setting? And the list actually goes on very long, and these are just a few examples that I'm listing here due to time limit. And furthermore, at the distributed level, we have also great challenges. For example, in this case, each agent makes local decisions. So how can we make sure that by making good local decisions, we can achieve good global decisions? So to summarize, then I've talked about the intersection of AI and the security, how we can do better AI in the presence of attacker. So maybe just with 1 minute, so this part is not really strictly related to representation learning, but given the discussion yesterday talking about as a community, what are some greater responsibilities we have, besides thinking about people losing jobs and so on, I think this actually is a very realistic challenge and issue that we have. So I want to just spend the last 1 minute to talk about this. So far for the AI and security, what I've been talking about is the first part, is how in the presence of attacker, right? So how attackers can attack AI, which is causing the learning system to do the wrong things, right? But on the flip side, there's another part of the intersection between AI and the security, which is how attacker can misuse AI. And in this case, the attacker can misuse AI to attack other systems. Whereas to prevent the attacker from attacking AI, we just need security for learning systems. We just need to figure out how to build better, stronger security systems. But when the attacker is misusing AI to attack other systems, we actually need security in other systems, which is an even harder task. And there are already some examples where, for example, deep learning can empower bug finding. There has been some recent work on this, and also deep learning can empower, for example, phishing attacks by just looking at using deep learning system to look at your social media and so on. And some of you may have seen this, right? So this is an example from Cambridge Analytica, which has been essentially people have contributed the success of Trump to this, right? So this is where essentially these AIs, I mean, they probably have not even used as sophisticated AI techniques that we discuss here. But as you can see, going into the future, these type of AI techniques could be misused for large-scale automated targeted manipulation. And again, that's just one example. And really what we see here is that there's asymmetry between attacks and defense, and also AI progress is uneven in different areas, which can allow attackers to misuse AI to launch attacks, which will have severe consequences. So, and I won't have time to go into the details, but right, so there are many challenges why this is a challenging task, and ultimately this is a dual problem. Stronger AI can help us, but also at the same time can make attacks easier and stronger. So, right, to summarize, then I think this is a wide open question. You can compare this to nuclear weapon, where treaty actually can help, and detection in that setting is possible. But when attacker is misusing AI, some of these actually, treaty doesn't help, and the detection will be very, very hard. And hence, right, to summarize, I think as a whole community, not only that we have a strong responsibility to figure out how we can build better security for these learning systems, to have the learning system generalize better and have better provable guarantees. And also, I think at the same time as we develop AI techniques, it's also good to think about what other techniques and approaches that we can investigate to figure out how to prevent the misuse of AI for attacks. And as people can see, that already it has led to severe consequences. So to summarize, I strongly believe that security will be one of the biggest challenges in deploying AI. And for all of us, I think there's a lot of work ahead of us. Okay. Thank you.
Chris, actually, I was going to say.
Yeah, no, I'll concept, but
you have a question too.
I have a question.
Okay.
This idea of an adversarial example seems to be based on like human psychophysics. So we have things that we perceive to be different or the same, and this is just our brains. But if we had brain Jacobians and used, like Jan talked about optimal control yesterday, where you backpropagate through a system that has a dynamical system, and then you decide what you should do best. We could do the same thing with our brains to find. Couldn't we do this? I mean, if we had.
No, she didn't report it, but you can try to train it against adversarial examples, and it doesn't work.
I know, but what I'm saying is you could construct adversarial examples in human space. So there are always adversarial examples. The question is, are they, and we would probably call them illusions. So
it's an optical illusion.
Yeah, so what we want is a model that gets at that has the same illusions as people, not different illusions as people, right? So isn't this just another way of saying we need our models to act more like humans and less like, not humans, which is sort of the point of machine learning?
That's a good question. You should set up. So I think there are a couple points to that. One is that, again, that's why I was talking about this representation. So clearly these adversarial examples to humans, they are now adversarial examples in the sense that the humans will see these the perturbed images just like the original image. So in that sense, also as showing that the representations that these neural networks are learning, again, humans don't have this type of problems. And hence, the representations that we are currently learning in these neural networks do not have the desired properties that's right. Maybe the human systems have, or just in general, this kind of smoothness that we want. And also, in addition to that, so far, I think these examples are shown in the sense that whether it's in comparison to how humans would respond. But I think in other settings, you can talk about adversarial examples in other settings as well. It's just so far that has been the main focus.
So we'll take more.